Good afternoon, welcome back. This is now going to be lecture 38, and so we are approaching the end of our course here, but we have still got a little bit of material to cover. So, I am going to go about 3 or 4 lectures more and try to give you take it to a point where you have a reasonable feel for cyclic codes. So, what I have done is just to speed things up, I have written out lecture 38 and I will read through it, and that will help us save a little bit of time. Now, let us just quickly recap. So, what we did last time we were talking about finite fields, and although I had labeled the lecture finite fields a deductive approach, we really didn't get a chance to go into the deductive approach. We spent most of the time recapping our earlier discussion on construction of a finite field, but we completed that. And so, at the end of the last lecture, we were just ready to begin discussing the deductive approach. So, where we had left off is that we are actually provided a construction of finite fields, okay, and the way we did it was saying that you can always take the generic construction is like this. You actually look at the set of all polynomials over a certain finite field f p, and then you go modulo an irreducible polynomial, and this really should be interpreted as the collection of equivalence classes, where we define 2 to be equivalent if f x divides the difference. We found that this yields a field, and towards the end of the last lecture what we did was we took an example, and in the example the characteristic was 2, the irreducible polynomial was x 4 plus x plus 1, and then we carried it out, and I showed you explicitly the finite field in this form, where I actually showed you how the elements of a finite field look like. Okay. So, today we will actually go towards a deductive approach. So, I have just written out what I just told you here. So, let us begin with the deductive approach. So, the deductive approach assumes very little. It says, look, all that I know is that I have a finite field and that the finite field contains q elements. Okay, so, whatever this is a set, it is kind of like a black box, and I am trying to investigate what its internal structure is like. What I do know is that the elements form a field, that is, there are 2 operations which we call addition and multiplication, and under these operations the set together with these 2 operations forms what is called a field. And the other important thing that we know is that the number of elements is q. From this we want to actually deduce the internal structure of the group. So, what do we mean by the fact by using the structure of the field? Well, we know that f q plus must be an abelian group, and that if you take the set along under multiplication, it must satisfy the axioms of closure, associativity, the identity element, the inverse, commutativity, and there is also the matter of distributive. And in addition, we have that multiplication distributes over addition. Okay. So, we want to make use of this and try to deduce the structure. So, the way we will actually start is by looking at the identity element under multiplication. So, let us call that 1. Now, the finite field, since it is required to satisfy all these axioms, must contain a 1, which is the multiplicative identity, but if it contains 1, it must contain 1 plus 1, 1 plus 1 plus 1, and so on. So, in other words, it contains 1, 2, 3, and so on. But since this field is finite, this list cannot continue indefinitely. At some point there must be a repetition, because after all an infinite number of elements cannot be contained in a finite field. So, let us say that m is equal to n, and without loss of generality we can assume that n is greater than m. Now, just keep in mind that when I write m, what I really mean is 1 plus 1 plus 1 m times. Now, this now let me just say that from this it follows. So, from this it follows that n minus m is equal to 0, and the way you should interpret that is, because when you write m you really mean 1 added to itself m times, you mean that 1 added to itself n minus m times. The collection of n minus m ones when added together must give you 0. Okay. So, this motivates the definition of something that is called the characteristic of a finite field. The characteristic of a finite field is the smallest integer p such that when you take p copies of the identity element under multiplication, you will actually get 0. We have already seen that there must be some integer such that it is equal to 0. Now, we are saying let p be the smallest such integer such that p copies of 1 when added together will end up being 0. So, this is called the characteristic. The first theorem that we want to actually prove is that the characteristic of a finite field is a prime. In other words, the smallest number of integers of copies of 1 when added together to give 0 must be a prime. How do we prove that? Well, it is straightforward. Supposing this characteristic was actually a times b. That means you took a times b copies of 1 and added them together, and you obtained 0. That is equivalent to saying that a times b is 0. But if a b is 0, then it must be that either a is 0 or b is equal to 0. But then remember that since you factored a p into the form a and b into the product of a and b, it must be that both a and b lie between 1 and p. But then if a is 0, then that contradicts the minimality of p, because we said p is the smallest integer such that if you take p identity elements, copies of the multiplicative identity, then you will actually get 0. But here you are getting that either a is 0 or b is 0. So, that contradicts the minimality. So, the only way this could happen is if in fact such a factorization is not possible, which tells you that p is a prime number. So, p could be 3, 5, 2, 3, 5, 7, 11 and so on, but it cannot be 6, 9 or 12. Now, okay, so that was our first observation. So, to summarize, what we have actually seen is that there is a unique prime that is associated to a finite field of q elements, and that prime is called its characteristic. Now, we are going to explore that a little bit further. So, well, we say f q therefore contains 0, 1, 2 all the way up to p minus 1, and we know that p is 0, which means that if you just, so here is f q and here is these elements which are actually a subset of f q. Okay. Now, the arithmetic that you use to operate on these elements is mod p arithmetic, because for example, if you add 1 to p minus 1 you will get 0, right, because we know that p is 0 in the finite field. So, that means that when you work with these elements and you under the two operations addition and multiplication, what you will be doing is virtually mimicking the operations that you would carry out in a finite field of p elements, that is Zp. So, Zp is something that you are familiar with. So, this subset of the finite field really behaves like Zp. So, that means the picture that you now have is that inside your finite field Fq, you have this subset which is Zp. Only thing is that instead of calling it Zp, we will now write Fp, because our preferred notation now is to use f to denote a finite field and let the subscript denote the size. Okay. So, that means that sitting inside a larger finite field, we have a smaller finite field. Okay. So, let me just make that adjustment here and write f instead of z. So, now we have a larger field containing a smaller field. Now, in general, it can be shown that whenever you have a situation in which you have two fields E and F with E containing F, then it can be shown that this E is a vector space over F. Okay. So, this is true in general. Okay. So, it is not for this particular situation. So, whenever you have the situation that you have a finite field E containing a second finite field F, it can be shown, and it is not difficult to show, you just have to go through the axioms that go into defining a vector space. So, the larger field will be a vector space over the smaller field, which means you can think of the elements in the bigger field as if they were vectors over the smaller field. Now, in particular, that means that in our situation here, it means that the finite field of Q elements is a vector space over the finite field of P elements. But there is an interesting property that we can call upon here with respect to vector spaces, namely that since you can describe all the elements in the finite field like this, that is, you can say that you can take a basis for the vector space over the field. So, you can take a vector space for this vector space over this field, let that basis be gamma 1 through gamma m. So, I am actually letting m denote the dimension of this vector space, that is why the basis has m elements, but the property of the basis tells us that every element in the vector space has a unique expression as a linear combination of the basis elements. That means, the elements in FQ can be written in the form sigma ai gamma I is equal to 1 to m. Now, I have put an underline here just to emphasize the fact that we are thinking of these elements gamma I. So, these really belong to FQ. Okay. So, these elements are elements of FQ, except that just to emphasize the vector nature of these elements, I am actually putting a bar underneath this. Okay. So, now, but then the moment you write this and you realize that look, there are p choices for each of these coefficients, I can actually count. I can say look, this finite field on the left has q elements. On the other hand, if I look at the size of this set and I know that every such linear combination is distinct, how many possible linear combinations are there? Well, I have p choices for A1, p choices for A2, p choices for Am. So, the total number of them is p to the m. So, it follows that the size of this finite field is p to the m, but the size of the finite field is q. So, it must be that q is p to the m. All right. So, to summarize, what that tells us is that every finite field FQ must have size which is of the form q equals p to the m for some prime p m greater than or equal to 1. And moreover, we can actually say what this prime is. Moreover, p is the characteristic of FQ. So, in summary, every finite field FQ must be of size p to the m, where p is its characteristic. So, that means that you cannot have finite fields, for example, of size 12, because 12 is not the power of a prime. So, what are the possibilities? So, the possibilities include, so q for example could belong to 2, it could belong to 2 squared, it could be 3, it could be 3 squared, it could be 2 cubed and so on, it could be 5. So, always it has to be a power of a prime. Okay. So, now up to now we have deduced two things. First of all, that there is a unique prime that is associated with every finite field, and that prime is called the characteristic of the finite field. And in terms of the finite field, it means that if you take p copies of the multiplicative identity and add them together, you will get 0. So, that is how you pull out p from the structure of the finite field f q. Then the second property is that the finite field f q is a vector space over the set 0 to p minus 1. That set actually forms a smaller field f p, and since f q is a vector space over f p, it must be that q must be a power of p. Now, what we want to do is we want to delve into the multiplicative structure of f q. What does that mean? We want to focus on multiplication now. We are not going to talk so much about addition, and we want to see what we can actually say. And the beauty of this is that we are going to build up to a very simple picture. That is the best of all things. You work very hard, but at the end you get a very simple picture of the finite field, and that is the kind of a thing that you would like to have happen. You do not want to work very hard and come up with a very complicated picture. Okay? So, we are going to work and extract a very simple picture of a finite field. So, here let beta belong to f q star. Now, this star notation here simply means that we are going to look at f q, but we are going to exclude the element 0. In other words, f q star is notation for all the non-zero elements in f q. Then f q star contains, it must contain 1, which you can regard as beta to the 0. Okay, so, that is beta to the 0 here. It contains beta, beta squared, beta cubed, beta to the a, beta to the b, and so on. But this is an infinite sequence. But this finite field after all is finite. So, therefore, at some point you must have repetition, that is, for some pair of integers a and b with b greater than a, beta to the a must equal beta to the b. Okay, beta to the a is equal to beta to the b, but that is equivalent to saying that beta to the b minus a is equal to 1. Okay, so, now what that is telling us is that you take a non-zero element in f q, you can, for every such element there exists an integer such that if you raise beta to that power you will get 1. And so, now you are led to the following definition: the multiplicative order of beta is the smallest exponent e such that beta to the e is 1, because we already know that there is some integer such that beta to that integer is 1. So, now we are asking what is the smallest integer with that property, and that is called the order of beta in f q. Now, lemma 1, let beta in f q star have order e. Let us assume that the order is an integer e, and supposing someone tells you, by the way, I just discovered that beta to the L is equal to 1, and this lemma is telling you, well, the only way that can happen, if when e is the order and beta to the L is equal to 1, the only way that this can happen is if e divides L, and if e divides L, this is going to happen. How do we prove that? Well, what we do is we take L, we know that beta has order e. So, the smallest integer to which you raise beta is e. So, L must therefore be greater than or equal to e. So, it makes sense to actually divide L by e, and let us say that v is the remainder. And we know that from Euclidean division, or from our, which is our everyday integer division algorithm, we know that you can actually divide it to get a quotient and a remainder, and that the remainder is strictly less than e. It can only be as large as e minus 1. So, now from this we can say that therefore, beta to the L is beta to the u e plus v, which is beta to the u e times beta to the v. But this can be rewritten as beta to the e to the u times beta to the v. But beta to the e is 1, reason being that we have defined e as the order of beta. So, by definition beta to the e is 1. So, that is 1 times beta to the v is beta to the v, which is 1. Why is that? Because by the hypothesis of the theorem, beta to the L is equal to 1. So, beta to the L is equal to 1. which implies that beta to the v is equal to 1. But wait a minute, when we wrote this expression down, we noted that v was strictly less than e. But how can that be? Because after all we said that beta has order e. So the only way all these facts can be consistent, simultaneously consistent, if in fact v is actually 0. If v is 0, then there is no contradiction, because beta to the 0 is 1, and when you define the order you exclude 0. Okay. So the multiplicative is the smallest, so maybe I should have clarified that here. Let us put that in, is the smallest non-zero exponent e such that beta to the e is 1. So that tells us that e divides L. Okay. Again, to summarize, if beta has order e and beta to the L is equal to 1, the only way that can happen is if e divides L, and conversely if e divides L, this will take place. Now there are a couple more lemmas which are somewhat technical in nature. Again, I just want to keep you motivated by telling you that if you are patient in this phase, then eventually you will come to a very simple picture of the finite field. So lemma 2 says that if beta has order e and you raise beta to the power L, then beta to the L has order e divided by the greatest common divisor of L and e. And so just to illustrate, so perhaps I will just do a side calculation here. So we will actually say that, supposing, let us say that e is 15 and L is equal to 10, then what it is saying is that the order of beta to the 10 is 15 divided by the greatest common divisor of 15 and 10, which is the greatest common divisor of 15 and 10 is 5. So this will end up being 3. Okay. All right. So this was just to give you an example. I won't prove this, but have left this as an exercise for you, and the exercise is straightforward. Then we come to an interesting lemma which says that, look, if beta and gamma are two non-zero elements in the finite field, and let us say that a is the order of beta and little b is the order of gamma, then if a and b are relatively prime, that is what this is saying, their greatest common divisor is 1, then beta times gamma has order equal to ab, the product of the orders. And how do you prove that? I think that the proof is actually written down here. It is a little bit technical, so I won't actually go through it. You can read it on your own. It is provided to make your notes more complete, but rather than rush you through a lot of technical details, I will try to give you the overall picture, and the details are there in the writing. Okay. So let us just try to focus on understanding what this lemma says. It says, take two non-zero elements and let us say that their orders are a and b, such that a and b are relatively prime. Then it is saying that the product of the two elements has order equal to the product of the two orders. Okay. But the key point is that the two orders are relatively prime. Okay. How do you use that? Now, well, it turns out that you can actually use this to show that amongst all the elements in FQ star, let us say that there is an element beta whose order is the maximum. What does that mean? It means that you are looking at all the elements in the finite field and you are looking at all their orders, and you want to pick the element that has the largest possible order, and let us say that that is beta, and let us say that its order is r. then there is an interesting claim that the order of all the other elements in the finite field must divide R. Okay. So, for example, if we go back to our lecture of last time, here are the 16 elements of the finite field of size 15. You notice here that alpha to the 15 is 1. So, alpha has order 15. It turns out that the largest possible order in this finite field is 15. And interestingly, what that the claim was saying is that every non-zero element, so you exclude the 0, every non-zero element in the field must have order that divides 15. So, you can actually verify, for example, that alpha to the 5 has order 3, okay. Alpha to the 7 has order 15, alpha to the 3 has order 5. So, all the orders actually divide 15, and that is the content of this claim. Okay. So, every element has order that divides R, and the distinguishing feature of R, just to keep in mind, the distinguishing feature of R is that it is the maximal order of a non-zero element. And again, there is a proof written out here. The proof is again technical, so I will actually skip it, but it is written out in case you want to follow through with the details. Okay. So, then what have we shown up to now? What we have actually shown is, so this lemma here, lemma 3, was used to prove lemma 4. It was used to prove the claim. Okay. So, let me just make a remark here. So, we will just say that the proof here is via lemma 3. So, lemma 3 comes into play in actually proving this claim. All right. Now, we come to another lemma, and what the lemma says is that, well, you know, earlier you were talking about the maximal order of an element and you called it R. Well, the truth is that if the finite field contains q elements, then I can tell you what that maximal order is. That maximal order is precisely 1 less than the size of the field. So, in other words, the maximal order here is q minus 1, which is p to the m minus 1. And that is in agreement. For example, here in our last lecture, we had a finite field of 16 elements, right. The finite field looked like this. It contained 0 and all the other elements were powers of some element alpha. So, this is the very simple picture of a finite field that we would like to deduce. And what the lemma that we were just looking at says is that in a finite field of 16 elements, the maximal possible order that any element can have is 15. And that is what this, and what this table is saying is that, well, alpha here has order 15, so it has maximal possible order. So, we have identified an element of maximal possible order, right. How do you prove that? So, the proof is straightforward. Let beta have maximal order R, and we want to show that this R is q minus 1 or p to the m minus 1. Now, since theta and fq star if theta belongs to fq star, then theta must have order dividing R, which means that theta to the R is equal to 1, which means that theta is a 0 of the polynomial x to the R minus 1. But theta was just any arbitrary element in fq star. So, that means for every non-zero element in fq is a 0 of x to the R minus 1. But the fundamental theorem of algebra tells us that if you take a polynomial whose degree is R, it can have no more than R zeros in the field. Therefore, it must be that R is greater than or equal to p to the m minus 1. On the other hand, if you consider 1 beta, beta squared, increasing powers of beta, again for some pair AB, beta to the A must equal beta to the B, with B minus A less than or equal to P to the m minus 1, because the finite field contains only P to the m minus 1 non-zero elements. So, by the time you reach P to the m minus 2, you've achieved the maximal possible count. So, thereafter any element that you get must be a repeat of some earlier element, and therefore, it must be true that the difference between B and A must be less than or equal to P to the m minus 1. Therefore, the maximal order must be less than or equal to P to the m minus 1, because this here is equivalent to saying that beta to the B minus A is equal to 1. Okay. So, beta to the B minus A is equal to 1, but R is the order. So, this must be greater than or equal to R, right. So, B minus A, so we know that from this sequence here that B minus A is less than or equal to R, P to the m minus 1, and R must be less than or equal to this. Therefore, R is less than or equal to P to the m minus 1, but we just showed that R is greater than or equal to it. So, the conclusion is R is equal to P to the m minus 1. Now, it is possible that went a little faster than you might have liked, but the end result is easy to keep in mind. It just says that, look, if you are looking at all the elements, non-zero elements in a finite field, you look at all their orders and you pick the largest order of a non-zero element, that number is precisely 1 less than the size of the field. So, the corollary, with this now we have our very simple picture of the finite field. The picture is that, first of all, every finite field contains an element whose order is q minus 1. Let us call that element alpha. In terms of alpha, Fq has the very simple representation as being the union of 0 together with all the non-zero elements in the field, and every one of them can be represented uniquely as some power of alpha, where the power I ranges between 0 and q minus 2, because there are q minus 1, there must be q minus 1 elements in here. Okay. So, that is our beautiful representation of the finite field. An important definition here, we will frequently speak about, make reference to a primitive element of a finite field. So, an element alpha whose order is equal to q minus 1, in other words whose order is the maximum possible, is called a primitive element of a finite field. So, the word primitive is used in the sense that it can be used to generate all the other elements in the field, right. So, it is primitive in the sense that it is a basic element from which you can build all the other elements, and you can see that here, except apart from 0, all the non-zero elements in the field can be obtained simply by taking the various powers of alpha. Now, let us look at an example. So, supposing this was the example that we looked at last time. So, P was 2, the irreducible polynomial is x4 plus x plus 1, and we can either regard this as a collection of equivalence classes and use alpha to denote the equivalence class of x, or alternately one can actually regard alpha as an imaginary element that satisfies alpha 4 plus alpha plus 1. What that does is that if you keep this in mind, then you do not have to keep carrying this around, because your element alpha has in a sense this condition that you are doing arithmetic modulo x4 plus x plus 1 inbuilt. because alpha 4 plus alpha plus 1 equal to 0. This is more practical. So, here again is an example calculation. So, you can see that as you take the various powers of alpha modulo making use of this relationship, you can derive you find that you get all the distinct elements in the finite field, and not only that, you recover them under two representations. One representation is the one in which the non-zero elements are powers of alpha, which is this. The other representation is one in which every element in the finite field is a polynomial in alpha of degree less than or equal to 3. Right? You can notice that everything eventually reduces to a polynomial of degree less than or equal to 3 with binary coefficients, and you know that the number of polynomials whose degree is less than or equal to 3 is 2 to the 3 plus 1, which is 16. Okay. All right. Next, what we want to actually talk about, now that we have built up this simple picture of the non-zero elements in the field, we want to build up to a different picture. Okay. And maybe what I will do is, to motivate this, let me introduce a page here. Okay. So, what I want to do here is give you a preview of what we are trying to do next. Now, we are going to look again. So, I will say minimal polynomials and I will say by example. And in this example, you are going to have characteristic 2 f of x is x4 plus x plus 1. Our finite field of fq is going to be f2x mod x4 plus x plus 1. And we know that an alternative way of looking at it is that fq is precisely the set of all polynomials ai alpha to the I is equal to 0 to 3, where the ai are either 0 or 1, where alpha is by definition the equivalence class of x in f2x mod x4 plus x plus 1 and hence satisfies alpha 4 plus alpha plus 1 equal to 0. Now, it turns out that if you can organize the elements in the finite field in the following way, you can take the element 0, you have 0, you have 1, you have alpha, alpha squared, alpha 4, alpha 8, alpha cubed, alpha 6, alpha 12, alpha 9, alpha 5, alpha 10, alpha 7, alpha 14, alpha 13, alpha 11. So, this is the collection of all elements in the finite field, and at first glance this looks like a rather peculiar way of organizing it. It does not seem to have any structure, but we will actually see what the structure is. First of all, we want to identify with, so these so this is a bunch of 4 elements. It turns out that all these elements share the same minimal polynomial. What is that minimal polynomial? So, here you may think of this as being your beta, and here what I am going to put down is m beta of x. So, it turns out that m beta of this is just x, this is x plus 1, here you have x 4 plus x plus 1, x 4 plus x cubed plus x squared plus x plus 1, x squared plus x plus 1, x 4 plus x cubed plus 1. So, this is the structure in terms of minimal polynomials. And so, of course, you knew that every element has a minimal polynomial, and we already knew that alpha had minimal polynomial. I mean, we knew that alpha was a 0 of x 4 plus x plus 1. So, what this is telling you is that alpha has this as minimal polynomial, but it shares the minimal polynomial with all these other elements. So, you can actually interpret that as telling us that in fact what is true is that x 4 plus x plus 1 can be factored according to x plus alpha, x plus alpha squared, x plus alpha 4, and then you also have x plus alpha to the 8. So, that means that this collection of 4 elements are precisely the zeros of this, and you can write down a similar statement. So, perhaps I will just get rid of this line so that you can see things more clearly. Right. So, a similar statement can be made about all these other collections. So, that means that the 4 zeros of this are precisely these. So, we are leading up to this. So, you have this rather nice structure for the finite field. What characterizes the polynomials that appear on the left are 2 things. One is that every one of these polynomials is irreducible, that means it cannot be factored. Secondly, if you look at the degrees of these, you have degree 1, you have degree 4, and you have degree 2. It turns out that every irreducible polynomial whose degree divides 4 appears here. So, where does 4 come into the picture? Well, 4 comes into the picture because after all you are dealing with f of 2 to the 4, okay? And it is this 4 that is actually causing these degrees to be either 4 or else, interestingly, divisors of 4, and this is always going to be the case. So, if you have f of p to the m and you write down the minimal polynomials of all the elements in the finite field, you are going to get polynomials over f p whose degree divides m, and you are going to get all of them. Okay. And along with this, you also have the accompanying statement that since we know, therefore, x to the 16 minus x is x times x plus 1 times x squared plus x plus 1 times x4 plus x plus 1 times x4 plus x cubed plus 1 times x4 plus x cubed plus x squared plus x plus 1. Okay, so, there is a dot in here. So, that means that you can factor x to the 16 minus x into the product of irreducible polynomials. These irreducible polynomials have the property that their degrees divide 2 to the 4, and the 4 comes because 16 can be expressed as 2 to the 4. So, in fact, it may be better for us to actually write this 16 over here just to emphasize that fact. Let us write this as 2 to the 4. Okay. Okay, so that is the picture that we are trying to build up to. So, now having motivated the discussion of minimal polynomials, let us go ahead and look at how we would introduce this. So, the way we start out by our discussion on minimal polynomials is to say, look, every element, non-zero element in FQ is a 0 of x to the q minus 1. We have already seen this because the maximal order is excuse me, a small typo here, this really is x to the q minus 1 minus 1. Okay. We know that the maximal order is q minus 1 and that every element has order dividing that. So, a consequence of that is that every non-zero element in the finite field is a 0 of x to the q minus 1. So, the only element missing in this description is the 0, but 0 is a 0 of x itself. So, by multiplying this by x, we can make now the uniform statement that every element of FQ is a 0 of x to the q minus x. Okay. So, now given a non-zero element, given an element in the finite field, there is an associated polynomial of which that element is a 0. So, then it makes sense to actually define the minimal polynomial m beta x of beta in FQ star is the smallest degree monic polynomial of which beta is a 0. We know that every element is a 0 of this, but maybe this is not the smallest degree polynomial of which that element beta is a 0. So, let us look for that, and that is called the minimal polynomial of beta, and it is written as m sub beta of x. So, in our just concluded example, okay, so these were these polynomials m beta of x. We had all of these. These are the smallest degree polynomials. For example, if you asked what is the smallest degree polynomial of which alpha to the 6 is a 0, then the answer is this. So, this would be m beta of x when beta is alpha to the 6. The first lemma says that look, m beta of x is irreducible. Now, why must that be? Because supposing the minimal polynomial was not irreducible and that it could be factored into the product of two polynomials, each of whose degree is less than the degree of m beta, then because m beta of beta is 0, that means that the product of f beta and g beta is 0. So, either one of them must be 0. But these polynomials are of degree less than the degree of m beta, but we already said that this is the minimal polynomial. This is the least degree polynomial of which beta is a 0. So, that is a contradiction. So, the only conclusion that we can draw there is therefore, it must be, it cannot be that you can factor m beta of x, so it must be irreducible. So, the minimal polynomials are always irreducible, and in fact, we actually saw that, right, because I already told you that in this listing here, all the polynomials that you are seeing here are irreducible. So, that lemma just told us, well, that must always be the case. Then the second lemma is that, look, supposing you have the minimal polynomial m beta of x, and supposing you somehow find out that f of beta is 0, then the only way that can happen is if m beta of x divides f of x. That is, the minimal polynomial of beta in a way is very possessive, because it says the only polynomials which when evaluated at beta will give 0 are those polynomials which m beta of x divides. Okay. How do you prove that? So, basically you use the Euclidean division algorithm. So, you take this f of x of which beta is supposedly a 0, right. So, that is the hypothesis of the lemma. Then you use the Euclidean division algorithm, divide it by m beta to get a remainder. So, f of x is ax times m beta of x plus bx. Now, ax here is the quotient and bx is the remainder. You know that f beta is 0, which means that a beta m beta beta plus b beta is 0. But since this is the minimum polynomial of beta, we know that this is 0. So, this can only happen if b beta is 0. But then again, look, this b of x is a polynomial because you are doing division whose degree is strictly less than the degree of m beta of x. Now, either this polynomial is 0 or it is not. If it is not the 0 polynomial, then it would contradict the minimality of the degree of m beta of x, because m beta of x is supposedly the smallest degree polynomial of which beta is a root, is a 0, but you have just discovered that b of x has beta as a 0 and its degree is lesser. So, the only possibility is that b of x must actually be 0, but then when b of x is 0 and you look at this equation, you see that m beta of x must divide f of x. Okay, so, that is the claim of the lemma. We will put this claim to use right away, because we already know that every non-zero element is a 0 of x to the q minus x. Just a few minutes ago we dwelt on this, that every element of the finite field is a 0 of x to the q minus x. But we have just proven that the only way that can happen is if the minimal polynomial divides x to the q minus x. So, what that means is that we have shown that the minimal polynomial of every element in the finite field divides x to the q minus x. All right. All right. So, that is where we are with respect to minimal polynomials. So, so just to recap, so in this lecture what we have done is we have first looked at the multiplicative or structure of a finite field. Well, we are actually going through the deductive approach to finite fields. So, the first thing we established is that given a finite field of size q, there is an integer called the characteristic, and that characteristic is prime first of all. Then the size of the finite field must be a power of its characteristic 2. Then the finite field contains a primitive element, that is an element such that its powers generate all the non-zero elements in the finite field, and such an element is called a primitive element. So, that allows you to have a very simple picture of a finite field in your mind, one in which the finite field appears simply as the powers of some special element alpha, which is called a primitive element, and you can see the 16 elements spelled out here. Okay. So, in general we are saying that this would be the structure of the finite field. And after that, then we said, look, we can organize the finite field, the elements in non-zero elements in a finite field, or actually all the elements in a finite field, in a different way. We can kind of classify them and group them together according to their minimal polynomials, that is, the minimal polynomial being the smallest degree polynomial of which that element is a 0. So, here are the 16 elements in the finite field of size 16, here are their associated minimal polynomials. Now, we have shown that each of these is necessarily irreducible, that each of these necessarily divides x to the 16 minus x, in general x to the q minus x. Okay, so we have shown that, and that is about where we are. I guess the other thing that we also know as a deduction is that, look, if you take x to the q minus x, we know that its zeros are all the elements in the finite field. On the other hand, the elements in a finite field are zeros of minimal polynomials. So, clearly there is a relationship between this polynomial and the minimal polynomials. So, it is going to take a little bit more of effort in the next class by us to actually show that this is the case. That is, in fact, that if you multiply all the minimal polynomials together of the finite field, you will get x to the 16 minus x. So, as I had said here, this was a preview. Okay. So, maybe I should emphasize that and put that in the statement here. So, let me write down preview, a preview of minimal polynomials. Okay. So, I think this is a good place to stop. So, we will continue, and it will not take us very much long to wind up our discussion on finite fields, and at that point we can start talking about cyclic codes. So, thank you.